Good morning. I hope your day has been going well. I appreciate you having me here bright and early this morning. What we're going to do today is we're really going to focus in on the midterm exam, which will be for you next Tuesday. So next Tuesday morning, 8:30, we won't do the problem set thing. We won't do the seminar self-quiz, actual quiz. The only thing we'll do is take the midterm. And since this is the first midterm, I think it's important to talk about. So the midterm exam will have 12 multiple choice questions and 4 short answer questions. The multiple choice questions will have 5 possible answers, and you just pick the one which you think is right. And there's only one possible answer, not 2, and stuff like that. Those questions, you can just put the answer down, no problem. But the short answer questions, I want to see your work, all right? I want to see how you set up the material. So don't just give me the answers on those, like actually show the setup, how you get the answer, stuff like that. The midterm will be for you Tuesday, next Tuesday in this room, all right, at 8:30. The following Tuesday must be 10:28. When you turn quiz 4 into me, I'll give you back the midterm, and it will have what I call a summary sheet. And it'll be the last page on your midterm, and it just says like how you're doing in the class as of this time. And check that page out, all right? Make sure that the scores I entered are the scores you actually got. I do make mistakes, it's true. Also, if you're missing a lab, it'll say that on there. You got to get your labs in. There's a lot of points just for turning the labs in, even if they're late. So all those things are definitely worth checking it out. Now, in addition to the midterm, next week will be the first of what I call an exam prep worksheet that's due. Exam prep 1 worksheet, which is right after problem set 3 in the companion, by the way. An exam prep worksheet is basically a single page, double-sided. And most of the questions on there, you get the question, the answer is given, and you just show your work in detailed steps how you go from the question to the answer. So you know what the answer should be. You see the question. I'm hoping it's not a big deal to go from the question to the answer. On the other hand, all right, you see number 3 and you're like, what the, Russell? I don't even remember this. This looks like a foreign language. By all means, reach out to me. Reach out to the AVID/LSC Center, your friends, whoever, because these are all skills you're going to need on the midterm, all right? The exam prep worksheet you'll turn in before you take the midterm. It should be good to go. I'm hoping it's not a big deal, but again, if you do see anything weird on there, let me know. The nomenclature lab we did last Tuesday will be due next Tuesday and stuff at 8:30. Also make sure that you bring a printed copy of the identification of an unknown compound lab. This is kind of a fun lab, but this is the first lab where goggles are required. So if you have a pair, definitely bring them. If you don't have a pair, you've got to use one of my kind of funky ones that are the common goggles. It's not a hard lab, but it is kind of fun, but we'll be dealing with lots of chemicals and stuff like that. Any questions on that? Yes.
Will we be able to have a small note card?
No. This is a completely closed book, closed note kind of thing. You'll have a periodic table and your calculator. Now, Jasmine, some calculators allow you to put notes inside or constants.
Okay.
I won't be checking your calculator. He says, sometimes I cough when I don't really have a cold. I'm trying to imply something, so hopefully. Anyway, also today around 10:15, earthquake drill time. Oh boy! So how this is going to work apparently is around 10:15, and I'm getting different times, whatever. Around 10:15, there'll be things with earthquake, and what we're all supposed to do is like get under the table or crouch down. You have the right to do what you want to do. But then we're all going to evacuate and go to the far parking lot. So how that works for us, we'll go out this door, we'll go up the stairs, and to one of the farthest parking lots against Kane, the busy road. And after a minute or so, they'll say, all clear, return to your work. We'll all come back here and be good to go. I will lock this door behind me. You're welcome to leave stuff here. On the other hand, if you want to take stuff with you, that's fine too. That's up to you. Never go. Questions on anything? Okay. So all of today is going to be essentially like a review for the midterm. And what I'm going to do is I'm going to show you different questions relevant to the material for Exam 1. Exam 1 is basically over chapters 1, 2, and 3, problem sets 1, 2, and 3. All right? So I'll show you types of questions that you might see on the midterm. I'll show the question. I'll wait for a few minutes for you to actually work on it yourself, and then we'll talk about the answer. If you have a iClicker, you can participate in that, or you can just do it on paper. It doesn't matter. But this will be a great way to kind of remind you as to some of the things we've looked at over the last problem sets and stuff. So, cool. All right. So, without further ado, here's a question that goes back to chapter 1. And this is a question on density. Density is the relationship between the mass of an object and the volume of an object. And if you know the density, there's cool things you can do. You can separate out compounds. You can also identify compounds, which is what we're doing here. So in this problem, we have an unknown metal, and we want to know what the density is so we can find the identity of the metal. And in this example, 33.2 grams of this unknown stuff is placed in 10.0 centimeters cubed of water. So you can see in the little pictures right there, there's like a before and after picture. So before it was exactly 10.0 centimeters cubed, and after the metal was put in, 22.3 centimeters cubed. So see if you can use this information to calculate first the density of the unknown, and then see which of those answers down there would be the correct density so you can identify it. We will talk about it in a few minutes. Okay, so on a problem like this, the density is the mass of the object divided by the volume of the object. Now this object is irregularly shaped, which means we can't figure out length, width, and height if it was rectangular. We also can't do a sphere or something like that. So what people do a lot of times is use the displacement method, which is Archimedes' system. The difference in the volumes, i.e. 22.3 minus 10.0, that's going to be the volume that the object occupies. So in the denominator of your calculation, you want parentheses 22.3 minus 10.0. And then in the numerator, the top of the problem, you want the mass, which is this number right here. And like you saw in the density lab, those are pretty chill. Just put them on the scale, figure out what they were. So in your calculators, 33.2 divided by 12.3, that should give you the value of 2.70 or so. And if you look on this list of densities, looks like it's going to be aluminum because the densities are pretty close. Good to go. Any questions? Sweet. Now, here are 3 temperatures found on the Earth, all right? And those temperatures are 256 Kelvin, 45 degrees Fahrenheit, and 29 degrees Celsius. And we do use different temperature scales on the Earth, for better or worse. I'd like you to put those in order of increasing temperature. So from the lowest temperature to the highest temperature. Now, anytime there's a Fahrenheit calculation involved, I will give you the equation, and it's 1.8 times the Celsius plus 32 is how you get the Fahrenheit. What number do we use to go from Kelvin to Celsius or Celsius to Kelvin? 273.15, that's right. So knowing all of this, let's see if you could put these in order from coldest to warmest. I would convert them all to Celsius, but you can do it any way you want. Cool. Okay, so on a problem like this, what I would do is try to get them all in the same scale, and you can pick which scale you want. I think that Celsius would be the easiest, but there's nothing wrong with converting them all to Kelvin or Fahrenheit if you want to. As an example of that, remember Kelvin temperatures will never be negative, all right, not in our class anyway. So to go from Kelvin to Celsius, you would subtract 273.15. You'll get a negative value of Celsius. So this one is actually colder than 29 Celsius. It's a negative Celsius when you do the math. I'll show you the math here in a little bit. So this one's pretty cold. 45 degrees is kind of an unusual one. 45 is this value. So 45 equals 1.8 times x, the Celsius temperature, plus 32. So the first thing you would do is you take 45 and subtract 32 from it, and then divide by 1.8. And all of those things would make 45 smaller and smaller. So 45 minus 32 is, I think, 15. And 15 divided by 1.8 is a small number as well. So the Fahrenheit temperature will be a positive Celsius, but it won't be that big. So this one's actually going to be right in the middle. This one will be warmer, and this one will be colder. So since we want it in order of increasing temperature, you want coldest first, hottest last. Answer D sounds about right. Now here's the actual math involved, all right? The Celsius temperature for the Kelvin value does come out to be a negative number, minus 17. I tried to roughly do the Fahrenheit temperature, and I probably didn't do a very good job, but you can see it's positive. It's not very big, though, not very big compared to 29 Celsius. 29 Celsius is actually the largest of these. So 256 Kelvin is the coldest, 45 is kind of in the middle, 29 after that. Yeah.
I did it backward. I did 5/9 times in parentheses 45 minus 32.
That's fine. 1.8 is 9/5. So the way I did it, really like dividing by 9/5. But you could then multiply by 5/9, and that's fantastic too. Yeah, no worries.
It's the same thing.
Yep, exactly. I like your way. Hold up. Other questions? Here's a value, 4 values, using the metric system. And these crazy metrics are so important to what we do. I'd like you to put these in order of increasing size. So start with the smallest one, and then have the biggest one last. Now, what I would do on this problem is I would turn everything into meters. And you've already got 2 meter value. 0.125 will be before 2.3. So what you kind of need to do then is figure out how millimeters relate to meters and how centimeters relate to meters. And if you can do that, then you can put them in order of increasing size and be good to go. So see what you can do with this one. We'll talk about it here. The metric prefixes are great in chemistry and lots of fields of science for that matter, because they can represent large and small numbers pretty succinctly. And so like we've talked about in this class, kilo, centa, milli, micro, and nano are the 5 to know, all right? We've been dealing a lot with nano in the hydrogen lab. A nanometer is 10 to the minus 9 meters, stuff like that. But what we want today in this problem is centa and milli. So centa is 10 to the minus 2, and milli is 10 to the minus 3. So a centimeter would be 10 to the minus 2 meters, and a millimeter would be 10 to the minus 3 meters. So if you want to convert, say, 215 millimeters to meters, that's where this expression comes in. And what it says is 1 millimeter 10 to the minus 3 meters. So when you put this into your calculator, it comes out to be 2.15 times 10 to the minus 1, or better yet, 0.215 meters. All right, it's like you're dividing by 1,000 essentially. So this number, 0.215, is bigger than this number, which is 0.125, but it certainly is smaller than this one right here. Questions how I did this part? All right. So the centa is same kind of thing. You would take 9 centimeters, 1 centimeter on the bottom, 10 to the minus 2 meters on the top. This actually gives you 0.09 meters. So of all of these, 0.09 meters is actually the smallest one, 9 centimeters. So 9 centimeters is smaller than 9 centimeters, 0.09 meters is smaller than 0.125 meters. And as we saw over here, that's smaller than the millimeters value, and all of them are smaller than 2.3 meters. So answer D sounds legit. Any questions on that? Well, enough of that metric crap. Now let's talk about some chemistry, thank heavens. This particular, sorry, I should be more respectful to these things. Anyway, this is now more about the subatomic particles, like what's in an atom. And what I'd like you to do is tell me what is in an iron 58 atom. How many protons, neutrons, and electrons do we have? See if you can figure it out. So one thing you'll need for this problem is the symbol for iron on the periodic table. And what is the symbol for iron? Fe. Well done. If you don't know that iron is Fe, we'll have one of our periodic tables up there, and you can get there. The symbol is also listed as the name. However, if you know some of these, of course, it makes your life easier. Now, why you'll need that? Iron there is number 26. And what does 26 say about iron?
That's 26 protons.
Nice job, man. 26 protons. Those whole numbers up there are called the atomic numbers, and they represent the number of protons. So iron always has 26 protons. If you take a proton away from iron, then you have 25 protons. It's no longer iron. It would be manganese. On the other hand, you add a proton to iron, so it has 27, then it would become cobalt. So if it's iron, it will have 26 protons, totally. Now, a neutral atom has even numbers of protons and electrons. So our iron 58 here is going to have not just 26 protons, but it's also going to have 26 electrons to it. So the protons and electrons will be the same if it's neutral. Remember, protons are positive and electrons are negative. If they're equal, you won't have a net charge. And then finally, this number right here, 58, that's the mass number. It's the protons plus neutrons in this isotope of iron. So to figure out the neutrons, you take the mass number, 58, subtract the atomic number, which is 26, i.e. protons plus neutrons minus protons will give you neutrons, and it should come out to be 32. So answer B would be the right way to do it. Any questions on that? Awesome. Now, here's a question with two possible ways to solve it, and either way is great. We have some random element E, and E has 3 different isotopes. You can see that the first one there is number 72. It's about 54.5% of the time abundant. The second one, number 73, about 15%, and 74, close to 30%. Using those 3 values, I want you to find the most reasonable atomic mass value for the element. Now, atomic mass is the other number on the periodic table, usually with a lot more sig figs. And this is an idea as to where these numbers come from. So you can solve this either using like a number line to make a prediction what the best atomic mass, i.e. average value would be, or you can do this the math way. You can take 72 and multiply by 0.545 and add it to 73 times 0.156. See if you can figure this out. We'll talk about it here. Okay, so on a problem like this, there's two ways you can solve it, and either way is great. The non-math way invokes kind of thinking about what these things mean in terms of statistics. So notice that we have a lot more 72 than we have 73, i.e. this is much less than 15%. This is also much less than 50%. So the average, which is all the atomic mass is, it's an average of the isotopes, the average will be a number which is somewhat closer to 72, definitely, than like 74, all right? So it's probably going to be somewhere in this region, all right? If it was 100% 72, the average number, which is what we're calculating, would be really close to 72. If it was 100% 74, the average would be much closer over there. So just because we have more than 50% 72, it's definitely going to be over here in this region, all right? However, it's not like 90% plus 72. It's 50-ish percent 72. So I don't think it would be as close as 72.1. I think that would be a number you'd get if it was more like 90% plus. It's only 55%. So my money in thinking about it would be on B, all right? It's definitely a number that drifts towards 72 more than 74, but it's not 100%. That would be my hand-waving explanation. Now, if you're like, Russell, that really is lame. We need some hard numbers here. All right, no problem. You can also do this kind of setup, which is what I started for you. You take the mass of the isotope, like 72, and you multiply it by the decimal version of the percentage. So you don't multiply it by 54.5, but you multiply it by 0.545. And you'd add that to the mass of the second one times its decimal abundance, 73 times 0.156. And the last one here would be 74 times 0.299. That will give you a math number, and if that's the way you want to do it, that's totally fine. But either way, 72.8 seems like a pretty good call here. So again, you can either do math, just decimal version times its mass number, and add them all up, or you can kind of think about what the statistics are. And honestly, either way is fine. If you have a preference for one way or the other, that's totally cool. Any questions on that? Okay. Strontium forms strontium 2+. All the group 2A metals basically form positive 2. But what happens when the strontium 2+ ion forms? Look at these different descriptions and see if you can figure out what the best one would be for this particular example. So again, we're going from strontium to strontium 2+, and see which one of those would be the best description. Okay, so strontium on the periodic table is number 38. Strontium's named after a Scottish village or something like that. Whatever. 38 means 38 protons. And if the strontium atom is neutral, how many electrons will it have? 38. That's right, same number. So neutral strontium has just as many positive protons as it has negative electrons. So when you make strontium 2 plus, all right, you now have more positive protons than you have negative electrons. So what happens, and I think most people are pretty cool with this, 2 of the electrons leave strontium, all right? So the positive 2 comes from like 38 times plus 1 plus 36 times minus 1. You end up with truly a positive 2 charge. And 2 electrons are actually kicked out of the strontium. You can write them as products, as we'll do later. So strontium here is losing 2 electrons to make strontium 2 plus. And in the process now, instead of having 38 electrons, now it has 36 electrons. So if you go to the periodic table, number 36 right there is krypton. So now it has the same number of electrons as krypton. So answer C here would be the best answer. So it's losing 2 electrons, it's not gaining 2 electrons. It's not losing 3 or 1 or something like that. Cool. Any questions on that? Cool. Sometimes I talk about cool kids in the back of the bus. Strontium 2 plus has a noble gas configuration. Noble gas configurations are the cool kids in the back of the bus. And most of the time when you make the ions, they will want to be like the noble gases. So, all right. This next question, we're going to do a couple of them here, goes back to the Bohr model for hydrogen. And in the lab that we did last week, the hydrogen spectrum lab, in the Bohr model, there was the nucleus, and then there were these levels, n values. And an interesting thing about these n values is that one is closest to the nucleus, and they go up like that, but they get closer and closer to each other, all right? Now, what happens initially is electrons start off here close to the nucleus, and they gain energy to go up to a higher level. And this process is called an absorbance line. And absorbance, you go from a lower end to a higher end. Now, absorbance is actually a really cool technique, but it's endothermic, you don't see anything. And lights, which is what we're using like now, and the hydrogen bulb we use, it's actually the opposite process. You go from a higher end back to a lower end, and these lines are called emission lines. And that's really what we're studying in chapter 3, all right? It's going from higher end to lower end. And those things give off energy. It's the lights we see overhead and stuff like that. So in this problem, it says how many emission lines, higher end to lower end, how many emission lines do you have using the first 5 shells of hydrogen? So 5 to 1, I just drew, is one of the transitions possible, all right? There are some other ones. See if you can find out how many emission lines are possible, how many higher end to lower end transitions are possible using these 5 lines. We'll talk about it here. Okay, so the emission lines are exciting. Woohoo! It's like light, all right? The lights over us are basically like emission lines, all right? And the different elements inside even our light bulbs then cause these emission lines, which cause the light to use and stuff like that. But anyway, so the number of possible emission lines then, you can start like at n equals 5 and go to n equals 1. That would be one of the emission possible lines. But you could also do 5 to 2. You could do 5 to 3, and you could do 5 to 4. So that represents 4 transitions. Each of those arrows is one of the transitions, all right? But you really don't have to start at n equals 5. You could start at n equals 4. And you could do 4 to 3, 4 to 2, 4 to 1. That would be 3 more transitions. Then you go down to 3. There's 3 to 2 and 3 to 1, 2 more. And finally, you can have the 2 to 1 transition. So if you count up all those sloppy arrows I've made, there's actually a total of 10 emission lines possible. And all of those represent possible transitions within the hydrogen spectrum. Now, what we looked at in our lab, all of our lines ended up at n equals 2. So there was like 5 to 2, 4 to 2, 3 to 2, and also the 6 to 2. But the other ones are also cool. The ones that end at n equals 1 are ultraviolet. The ones that end at n equals 3 are infrared, for example. So they all have their purposes, but at least this allows you to see how many possible emission lines you could experience. Any questions on that? Okay. Now, the y-axis here is an energy axis. All right? And as we've seen, energy is related to frequency, Planck's constant times frequency. It's also related to wavelength, divided by wavelength. So energy, the length of the line, is proportional to frequency. The bigger the length of the line, the higher the energy, means higher frequency. And if you have higher frequency, you'll have lower wavelength. So in this question now, what I'd like you to do is I'd want you to find the highest frequency emission line. All right, it's related back to the energy. Energy equals h nu, and nu is the frequency. See if you can tell which of these would be the biggest frequency, the highest frequency. All right. So again, all about emission, higher N to lower N. And the N values get closer as you get higher and higher. So the 1 to 2 gap is bigger than 2 to 3, and 2 to 3 is bigger than 3 to 4. So it might be tempting to say 2 to 1 is a big gap. And it is a pretty big gap. However, it's not as big as if you start up on 5 and go all the way down to the top. So the length of the arrow, if you will, is bigger for 5 to 1 than it is to 2 to 1. And so that means the energy of the 5 to 1 is bigger than 2 to 1 or the other ones, and energy is proportional to frequency. So answer E here should be a pretty good start. So the length of the arrow is what determines energy. As the energy gets bigger, your frequency gets bigger, your wavelength would be smaller, although it didn't ask for that stuff. So, questions? Okay, let's take a quick break. It's about 9:19. We'll start back about 9:25. So stretch your legs and stuff, and we'll start up again.